that better? Can they hear me online? Okay. Yeah, so in August of 2000 is when my adventures with Loess began, and it's remained one of my research interests ever since. So I've listed here a whole bunch of people with whom I've worked on Loess in different areas in the world, and have been very, very fruitful in the thought process. So today, Dave started the transition going into with a little bit of continental, but we're going to leave completely the oceanic realm and go on land. And I'm going to be talking to you about Loess and Paleosol sequences in the global iron cycle. So you've seen this diagram already before. We've been talking about the global iron cycle all morning and last night as well. The bottom line is the cycling between ferrous iron and ferric iron. As it has already been said, in the ocean, iron plays a very key role in primary productivity. Sources are fluvial and glacial, and as Ali had pointed out, these sources tend to stay on near coastal regions in the ocean, and it's the aeolian sources that make their way out into the open ocean. On land, weathering releases the iron, making it available, and the bulk of the iron cycling occurs in the soils. And then erosion will produce some iron-bearing minerals that can then be available for transport elsewhere. So you can see from this diagram that the atmosphere plays a really central role in the cycling on a global scale and moving iron and minerals around. So the atmosphere and dust are very important. And as Dave already mentioned as well, they are also very key and important driver of climate because of their physical properties of being able to absorb and scatter radiation. We've already been through many of these already. They can also produce, they influence the distribution and lifetime of clouds. They can produce ice particles within the clouds, droplets that could lead to precipitation. So the dust in the atmosphere has significant climate effects. They also account for a substantial amount of reactive surfaces in the atmosphere that can be readily chemically altered, even during transport. So all of these mineral dust properties, one thing that was said a little bit already by Dave, is that they are highly particle size dependent. So for various reasons, the atmospheric scientists have focused a lot on the fine particles, as was already mentioned also. But there's increasing, and in climate modeling, almost all models consider mostly PM10 and finer, very rarely larger particles than that. But there's our increasing amount of observations, direct observations, that suggest that larger particles, coarser particles, are very abundant in the atmosphere, are being transported to longer distances than previously thought, and have properties that are just as efficient as finer particles at influencing climate. So a very nice review paper that you can go and check out kind of synthesizes a lot of these direct observations of particle size trapped on filters on balloons in the middle of the ocean, balloons up in the atmosphere. And there's images, I can't remember if it's figure 6 or 7 in this paper, with 100 microns and 200 micron size quartz grains that are found that were picked up on these filters in the middle of the ocean. So 20 microns is small, and it can, much larger particles can actually travel. So they estimate in this paper that actually 85% of the total dust mass probably is between 2.5 microns and 62.5 microns. They also highlight in this paper that there's a very broad heterogeneity in what fine, coarse, super coarse, how you quantify that with, so they propose in this classification here of fine being the less than PM, well, the PM 2.5, coarse, super coarse, and then giant. So if we look at this classification and compare it with very typical grain size distribution of loess on the left-hand side of the penultimate glaciation and a paleosol of stage 5, we can see that we have a mean distribution of the loess that's 50 microns, so we're in the upper range of the super coarse based on their classification. But there's also a continuum of all the grain sizes all the way to the finest in the loess. The same similar coarse particles are also found in the paleosol, which is logical because it's simply altered loess, diminishes obviously in total amount, and also a very logical shift to the peak to a little slightly finer median size. And the smaller particles, the less than 10 microns, are amplified in the paleosols. So if we look at these two generalized distribution and superimpose them on top of one another, it's really easy to understand that Loess and Paleosol sequences are actually, they provide a multiple facets of the system. Going from end members of the Loess units that archive the atmospheric mineral dust coming in, that can be from proximal sources all the way to fairly distal sources. In a given unit, this distribution would give you an indication, or you could interpret as being based on the distance of travel. From the mineral source, we can get information of the sources based on its mineralogy. We can also get wind directions and intensity. And then the other end member, we have our paleosols that are archiving based on all these new particles that will be formed in situ, the local climate. And we can interpret that based on the extent and the nature of the alteration that is occurring to produce these new particles. But the story is not, we shouldn't think of it as being so green and red, but really it's a continuum between all of this. In Loess units, we can also record or retrieve information about the local climate. And similarly, in our paleosol units, there is still information about the parent material, so the atmospheric mineral dust. So interpreting paleoclimate and paleoenvironmental or inferring can be quite challenging because of the imbrication of these. But when you attack that problem, you can take out of it really insightful information. For many years now, I've been concentrating a lot on European loess, and it really is a fantastic playing ground to try to untangle all of these different types of information, because the source of mineral dust across Europe is quite variable. The distribution of loess accumulation is also very variable, and the nature and extent of the alteration that can occur is also very variable. And this map that is showing a snapshot of conditions at the last glacial maximum exemplifies all this variability. You can see, so the ice sheets obviously are a source of control as to how extended they are and how dynamic they are. They will be producing material that can later be uplifted and transported. Sea level, on the map here, you see all the gray zones in the English Channel. That's all continental shelf that is exposed during glacial maximums. So significant amount of source of material that can get emitted and transported elsewhere. We also see on this map the purple line, the solid line is the permafrost, the perennial permafrost line at the last glacial maximum, and then the purple dotted line being the discontinuous permafrost line. So all these factors, when they come into play, they dictate the type of alteration and dictate where the loss is going to be found, the relief. So it really makes that every site is a unique area and can extract unique information. So I'm really going to focus today on you've understood by now, on Loess. So when we think of iron cycling in this kind of system, I'm sure that you all have paleosols in mind. Here we have two beautiful paleosols of the last interglacial 5E and then the 5C just sitting on above. And paleosols are obviously, without a doubt, where there's a lot of transformation and iron cycling occurring during the pedogenic process, which is controlled by the soil forming factors. Temperature and precipitation or water availability are important climate factors that are controlling. So you can see that this one location, that's the time that both of these paleosols have drastically different character, indicating different conditions under which they were formed. But I'm not going to talk about iron cycling in paleosols today. I'm not going to focus on that. I'm also not going to focus on this, but even in Loess units, visually, we can see that there's a lot of iron cycling that can happen, especially in periglacial environments. So this, you can imagine that when it was first deposited and accumulated, Loess is completely homogeneous. It does no really change. And here what we see is a cryoturbated surface. On the left is a vertical slice of that surface. In terms of scale, when you have the 1 meter stick, the yellow lines are 50 centimeters apart. And on the right-hand side, you have just a little bit further out in this quarry setting, a horizontal slice of this layer. So you're seeing on top here. Okay, so you can, sure that for those that are used to maybe some cryo kind of turbation stuff, this is really looking like a remnants of all these frost boils that you would have. So visual evidence that iron cycling does happen also in Loess. But I'm not going to focus on this either today. What I'm going to focus is on iron cycling or evidence of in Loess that shows very little or no expression of anything at the outcrop scale. So at the top of the section that you're seeing here is glacial stage 12 Loess from a section in Bulgaria. So all of the work that, and you can see, and it's sitting on top of obviously other paleosols. But in here, we're gonna look a little bit more of what's going on. But first, I'm just going to give you a couple of information about the site. We've been studying this site for a little while. It was the main focus of Christian Lag's thesis, who just defended earlier this spring. And this work is being done in tight collaboration with Diana and Nelly Jordanova at the Bulgarian Science Academy. So the Pleven is the red dot over there is in the lower Danube basin. It's about 70 kilometers away from the Danube. It's in a quarry setting. It has a series of 6 paleosol complexes below the modern soil and 7 intercalated Loess units in between. I'm not going to go through all the data. It's just to give you a little bit of an overview. So the whole section that we sampled is almost 27 meters. It was sampled at a 2 centimeter continuous resolution. There's a very beautiful tephra, 20 centimeters thick tephra that is highlighted there near the top in the L2 unit. For sake of time, I'm not going to show you the age model, but that was part of Christian's PhD work. So the whole section covers about between 800 and 900,000 years. And I'm sure that even without looking at what all the data is, your eyes can easily see that there's a drastic change in terms of the amplitude of how all of these different parameters are varying about midway through the section. Comparing the character of the variations across the two bottom soil complexes with respect to the ones above are marking a drastic change. And this change is occurring at the mid-Bruns climate event, which occurs at the end of, at the termination of glacial stage 12. So we're going to zoom in, like I said already, zoom in on this glacial Loess unit. So on the left-hand side, it's replotted here, the absolute difference in frequency of susceptibility in red, and then just the low field susceptibility in green. So we're going across the Loess unit, so we don't expect significant variations. The gray bands on these, you can see them, but you can block them out a little bit. They're all cryptotephras. Okay, so their parameters are behaving differently, but that's expected. In the middle panel is SIRM over chi. I'll show in a couple of slides the demonstration, but at this site, this ratio is giving us information as to the parent material and wind dynamics. So as the parameter gives higher value, wind dynamics increases. The blue data is DRS, so diffuse reflectance spectroscopy, goethite concentration or goethite content results. Again, for sake of time, I'm not going to go in, but if you have questions, we can go through that afterwards. And then on the right-hand side, we have also from the DRS data in black, the luminescence parameter. So as luminescence increases, the color is lighter. Luminescence, when with organic, generally changes with organic matter. As you have more organic matter, darker colors, less luminescence. And in the yellow is attenuated Fourier transform infrared reflectance spectroscopy. And from those type of data, you can extract calcite content, which is what was done. So quickly, what we are observing here is that if we look at our goethite content, it varies. In the early glacial, we see that when goethite content is higher, so these blue horizons that have been highlighted for you, they correlate with low calcite content. Okay, so in the earlier glacial, these variations are thicker. The cycles are thicker. As we move up into the hardcore glacial period, we're still seeing, but on a shorter depth scale of these intervals. The second thing that we're seeing is that, so there's missing, that's why the luminescence is there, because there were there were issues with the samples here. If we're seeing the in terms of calcite or the luminescence, which is following the calcite, we have higher concentrations or higher content, always located just underneath these high goethite horizons. So his hypothesis, Christian's hypothesis, looking at this data set through this glacial period, was that, well, goethite is maybe formed in situ, and that it's being formed in response to precipitation or water availability. So he wanted to attempt to demonstrate that this was true. So the first step would be to demonstrate that the goethite is actually not coming in with the parent material as coatings on the grains, but is actually being formed in situ, so that it is not dominantly detrital. That's what he had to try to demonstrate. So on the left-hand side of the plots, we have goethite content, again, the DR is derived, and it's plotted against a grain size index. So we would expect, if the goethite was being brought in with the parent material as coatings, that it would have some kind of correlation with our parent material sedimentological indexes. So the grain size index is the ratio of coarse silt to the combination of fine silt plus clays. As this grain size index increases, wind dynamics, more material is being brought in. So we can see that. So for the whole section, there's only 249 granulometry data that were required so far. But you can see from those already that there doesn't seem to be much of a correlation. The green dots are the samples that are within that glacial 12 unit that we're looking at more closely at the moment. In the middle plot, we're testing what I said already was our magnetic wind dynamic proxy to this sedimentological wind dynamic proxy. And it's not a fabulous correlation. It's not but you can see a tendency of going through a linear kind of increase. There's a linear correlation, but it's weak because we're seeing with two populations. But again, there's only 249 samples because we only have 249 grain size determinations so far of the 1,336 samples that we have for the full section. So with more data, perhaps these two kind of little poles that are pointing out will get merged. The current regression fit, if you did one for this, has an R of 0.68. So it's not horrible, but it's not great either for now. A sister site, Harlots, that's nearby. When we do this exercise, we have an R squared of 0.8. So we know that with more data, most likely we should be going in that direction. So if we keep the assumption that this is a wind dynamics, and for this parameter, we have every single sample measured against our goethite content, we can see that again, there's no real correlation between the two. In green is the stage 12, our unit, and if I had plotted all of them, you would see that most Loess unit, we have goethite content that are fairly invariable with respect to the wind dynamics proxy, and in Loess and Paleosols, we have a wind dynamic proxy that is fairly invariable with goethite. So the goethite is not predominantly detrital. It's not saying that there is no detrital goethite, but it's not predominantly detrital, and definitely in the glacial unit, we can rule out a detrital origin. So if we come back, we can interpret then that the variations that we're seeing in goethite content in combination with the calcite content, that we can interpret that available water and precipitation and or snow melt favors in situ goethite mineralization, and also the decalcification and reprecipitation of calcite in the horizon as directly below. I know I'm over time. I have 2 slides left. So if we take this information and then we try to extend across the entire record and attempt to quantify, the goethite derived data is, and the second plot from the top is in blue. So what Christian then did, which are then the black dots on that same plot, those are susceptibility of maghemite determined from KT curves, converted to mean annual precipitation using following the paper of Gao. So it's a transfer function that is not for this area, it's for the Chinese Loess Plateau. So this is known, it's okay. But then he took those data and converted the concentration of the goethite to mean annual precipitation. And that's the blue curve here with the quantified result. He then found an interesting study from a modeling study from Kraft et al. Don't know if I'm saying it wrong, but it doesn't sound good in saying it that way. So in this study, for all of the lower Danube, precipitation was modeled through time. And when you take the data in here for the data spot that was for Pleven, it's the black line, and you can't really deny that there's a very nice fit between the model precipitation data, even if you don't even look at the numbers of the quantification, just the amplitude trends are very good. And it happens that also the numbers, because they're on exactly the same scale, seem to match. So it seems that goethite at this site is being mineralized in situ through an iron cycling process that is assisted by water availability, precipitation, and that the goethite content provides for this site a paleoprecipitation record for the last 800,000 years for north central Lagroix. So this was a very nice result and an example of iron cycling in loess that is not periglacially deformed. So as a closing remark, Loess and Paleosols sequences have multiple facets. Sometimes the information can be difficult to untangle, but it's incredibly rich of information about continental sedimentary environments and climate. But getting robust interpretations of paleoclimate, paleoenvironment from these sequences do require to have a really good understanding of the interplay between the mineral dust, the incoming deposited material, where it's coming from, the iron cycling and weathering that is occurring, and obviously the climate, which is, yes, an information that we're trying to get out, but will influence what is there by influencing what mineral dust is going to be coming in, and so on and so on. Thank you.
Great. We have some time for some questions specific to the funds first, and then we'll come back to those speakers. Yeah.
Maybe by y'all.
Oh, well, for the Zoom people.
All the Zoom. That was great. Thank you. The saturation IRM is really not saturation. It's at 2 Tesla. I just wondered how much the goethite might have contributed to the SIRM in that. And then add on, how do you determine the goethite content? This TBA, is it done magnetically or what?
Okay, first question, the SIRM is 2 Tesla, and most likely the goethite is contributing not very much. It's all the hematite and everything else that would be in there. The TBA, the true band amplitude, like I said, is it's diffuse reflected, diffuse reflectance spectroscopy data that from which that is done. So this is already, so this is the spectra, it's the second derivative of the spectra already. Christian in a recent paper in Method X, he analyzed this in a very robust way, in the sense that he takes into account normally it's fixed wavelength that people use to determine what the amplitude is of the thing for your hematite. Knowing that the peak position shifts with respect to grain size, with respect to stoichiometry. So using a fixed wavelength position can lead to not as accurate. So he allowed, he scan and he would try to find the maximum and the true minimum, and that's why he called it the true band amplitude, because so it's a more, and if you want an example of how true that this really needs to be done, this plot here is the wavelength of the peak position for the hematite, as an example. Okay, so you can see that stratigraphically, that peak position in terms of wavelength varies quite significantly. And the variation is completely correlated to the stratigraphy. So this is telling you that it's shifting because it's a mineralogical change of that hematite. Grain size, maybe source, provenance, source difference, the pedogenic hematite with respect to incoming less detrital hematite. Yeah.
So have you done any low temperature demagnetization of RTSRM yet?
We've done a few. Christian was not he was really busy doing a whole bunch of other things. So he didn't do, there hasn't been a lot of low temperature data done yet on this sample, on this site. Our system was also down for a year and a half because the squid failed. Everything is back and running, but there's definitely a lot of, there's a lot of work still left to do on this really incredible site.
Yeah, so because one of the sites I was working on recently is Paleozoic, but one of the things that we noticed is that we'll have the stereotypical increase with a lower temperature in the RTSIRM, specifically in units that we believe to have a detrital origin of goethite versus more paleosol units where they still have goethite identified from other means, but they lack that increase in temperature. So one of our interpretations that it could be a pedogenic versus a detrital source, but yeah. So
Yeah,
something I would look forward to seeing.
We've done a lot of work on the nearby site Harlots. Yeah.
Andrew's got a question, and after that, if anyone's got any questions for France, otherwise we'll move on to all speakers.
France, thanks. So goethite is environmentally abundant and really important for all the reasons that have been talked about this morning, but magnetically really hard to detect. As you pointed out, 2 Tesla fields hardly touch it. People like Bruce and Pete seem to prefer Merspar, which makes sense. Your low temperature test makes sense, so it's interesting that question is asked. I'm curious on your perspective, because I think it's important for our community. We talk a lot about goethite, but we're hopeless at quantifying it, just because it's challenging. So I'm curious on your perspective about nano goethite, which I expect would be really common and abundant. I know you guys have worked on it. Whether the coercivity softened substantially in nano goethite compared to coarser stuff, and whether that gives us hope for magnetic quantification, or whether you just prefer to use DRS, which to me makes a lot of sense with the approach you use.
So most people know me by now. I have a gazillion amount of data that is unpublished. We have three different sites now for which we have a lot of DRS data, and for 2 of those also a lot of low temperature. I think for now the quickest and easiest and seems to be very accurate, especially if we modify how we use DRS and how we quantify, will be very quick and it's fairly accurate. In terms of magnetism, my perspective is that the best way to get something that would be comparable and inclusive has to be a low temperature, like 10K, like low temperature determination, because that's where it's the only way that you'll be able to have an inclusive view of the entire population of goethite. So up to now, the data that I have, if you go and use the difference of the different remnants after you've demagged at the low temperature and compare that to goethite content that you get from the DRS, it's on the order of the correlations that we were getting for the, so it's not perfect, but you're pretty close. Does all that effort really, does it?
So we should also all go out and buy DRS instruments. If we care about goethite. I mean, it's quicker and
it's quicker and
more
it's
precise. less expensive.
all of those. And and being able to then compare with other data that we can also produce that is more quickly. You get a more comprehensive global view.
What uncertainty do you get approximately?
What?
Uncertainties with the DRS quantification?
Okay, so there, the error bars are there. So for each data point, it's actually 5 measurements that are averaging, and you can see on the. Okay, so the error bars.
Yeah,
You
right.
can see on here. So
I think it's an important thing for our community to consider.
Hmm.
And so, you know, there are a lot of groups that use DRS almost exclusively for this purpose. And so I think for people to hear the message that DRS is a really valuable supplement is important.
but I also agree that DRS by itself is not going to give you all the view. It's good to put that into context, because you wouldn't know exactly where the goethite is coming from, and it's the global view. So, but yes, multidisciplinary.
All right, thanks, guys. We got about 10 minutes for questions for the speakers. I know there are a couple left over from each talk. So if you have a question for any of the speakers, just raise your hand and we'll throw those questions around.
Did I do something wrong?
I don't know why the general Zoom isn't showing right now.
Because I stopped share.
No, you're plugged into the projector, then that would explain it. Yeah.
All right, you just identify your speakers.
Why is it me?
I mean, I guess it sort of just continues some of these grain size discussions, but it sort of relates a little bit to Dave's talk. I guess particularly you sort of highlighted you sort of showed grain size dependent coercivity for hematites. I guess it was almost all within the achromatic zone, right? So in terms of where you go from being achromatic to actually scattering against the light, being on the order of one micron in hematites. So I guess I'm just sort of curious about that in particular for, I'm sort of thinking of the Dunlop and Osmeer paper where you're sort of, once you're sort of getting, sort of falling off around sort of 400 nanometers, then you're getting decreasing coercivity, whereas you were showing increasing coercivity rates kind of in those higher ones. But then you end up with this much broader coercivity spectra as you're going down into eventually into the SP. So yeah, I guess this sort of relates. I guess the question, and this is a little rambling, but you sort of talked about telling the difference between coating on a quartz grain versus that entire grain being hematite. And one of those differences there would be that one of them would be pigmentary and one of them would be that achromatic specularite. So I guess that's again to be sort of calibrating these the sort of spectra-based methods versus the magnetic methods.
Yeah, so I think I wasn't trying to be too specific with the examples, different coercivity spectrum. So I'm just demonstrating the challenges that we have that have just been discussed in terms of quantification of hematite and goethite. And we have these proxies that we use that we say, oh, that's hematite and goethite, but in terms of actually getting quantification, that's a very different thing. So I put those in just to make the kind of general argument, the challenges that we face. I agree completely about the grain size and reflectance relationships. Again, that's something not currently considered in climate models. So I think we can actually provide a lot of information into these models, dust modules, and how they're being used. The modelers use these phrases parameterization, which just means, I don't know, I'm gonna make some assumptions. And I think provide a lot of information to help with those optimizations.
In both those spheres are really, you need to decouple them. It's true that all the climate modeling part, they have more issues than just, just the composition, the grain size, which they're not taking into account, all these things that you talked about. With respect to DRS, when you have your own sediment, it's a completely different kind of, the problem, the beast is not the same. So I think there's a lot better control on what the DRS spectra of the sediment is giving you than when they're trying to do it on the actual atmospheric gas.
Just more of a general comment, and it's not necessarily directed at any one person. So anybody who feels like they have knowledge to share. But how much does the mineralogy and the way that iron is actually bound within dust particles change as a function of transport? So I know that there's a mineral component to dust, but then there's also small amounts of moisture that are absorbed onto the surface of those mineral grains that can either track more moisture or be ablated away or evaporated away during transport. And there's all kinds of ways that iron can actually be bound up into an agglomerate that isn't in mineral form, but is maybe organically bound. Along those lines, that may be a bioavailable one. Has there been much work on how dust particles evolve as a function of transport as they're moving through different layers of the atmosphere?
Well, Rich knows as well, probably much better, but it's definitely it's a question that the atmospheric physicists have. To try to understand exactly what kind of chemical alteration is happening in the atmosphere.
Sorry again. There's a lot of literature on atmospheric processing of iron oxides in the atmosphere, and you're absolutely right. It's the interaction, particularly with acidic clouds and things like that. Also depends on whether it's coming out of an urban zone, whether the dust is passing through a polluted zone of urban areas or not, for example. So, but yes, there is, and there's a lot of new work on the presence of different metals in dust, actually, that could promote or suppress the solubility of, for example, magnetite. And there's also photoreduction involved. So it's a really interesting and complex redox system in the atmosphere. So another issue with emit is that they're looking at what's in the ground, and good for them. It's nice. I mean, it's going to be a step, but let's say, but then the real issues of the effects, both in ocean fertilization and human health and nutrient delivery, depends on atmospheric processing.
All right, we've got two more questions. We'll try and squeeze in.
Yeah, I just wanted to follow up on that. The idea is that atmospheric processing, you have perhaps nano-sized conglomerates of hematite peroxide, that there is sort of rejuvenation where peroxide and hematite gets processed, releases that we think about. It rejuvenates very hydrogen and it ages back to how some clouds, but what stages in it gets dissipated out. And hydrogen is widely available.
All right, let's do one question from Ken as well.
It's actually really not a question, but just a very enthusiastic echo of the comment down here. We've done some work on Saharan ducts, looking at cloud processing. It's a hugely important process, and it is related to acidity. And what we found actually is that there's an enhancing of the reactivity of the iron and bioavailability. And so you're actually increasing that, and then you lose that when that material settles into the ocean because it's soluble. And so we've argued in a paper that we're about to submit about, that it may have stimulated carbonate production in the Bahamas. Other people had suggested that because of nitrogen enhancement of cyanobacterial activity, lowering CO2 and enhancing the carbonate by raising the pH, and even in the Amazon. So what sort of the Western expressions of those plumes of Saharan with the long atmospheric related processing is really, really critical. And there's still a lot to do with that, I would argue.
All right, well, thanks so much for a great session this morning. We're running right up on lunch, so I hope you'll join me in thanking our speakers again this morning. Logistics.